The purpose of this screencast is to teach you how to determine the most likely charge that an atom will take on when it ionizes. Firstly, ionization is when you have a transfer of electrons. Atoms will transfer electrons to get 8, and so this is the octet rule. Atoms react by gaining or losing electrons in order to obtain 8 electrons in the outermost energy level. And so here we have a model of a sodium atom and a chlorine atom. We can see in the outermost energy level, sodium, a metal, has 1 valence electron, or 1 electron in its outer energy level. Chlorine, however, has 7 in its outer energy level, so 7 valence electrons, chlorine being a nonmetal. Metals typically have less valence electrons, nonmetals typically have more valence electrons. And because they both want to get 8, chlorine is going to take an electron or receive an electron from sodium to get 8, whereas sodium will actually just lose its electron to get 8. And so if we take a closer look at how sodium is going to get 8 by losing an electron, you can see that if we lose this outer electron, it's going to expose its next layer down, its next shell down. It's kind of like an onion. You remove that outer layer, and then you have a fresh layer beneath it. And so if you take this sodium valence electron and it gets removed, the outer layer is now the next layer down, and it has 8, which satisfies the octet rule. Sodium wants 8, it gets 8 by losing 1. Chlorine, it has 7, it wants to get 8, so it gains 1, and so when it gains 1, it gets 8. And so using two different methods of loss and gain, both of these atoms are achieving a full octet in their outer energy levels, their valence shells. So metals typically lose electrons to become cations, sodium being an example of a metal, and then nonmetals typically gain electrons to become negative anions, and so chlorine being an example of a nonmetal. It's also important to note that whenever we form a negative ion, we change the suffix of the element to "ide." So we go from chlorine to chloride. So chloride ion, and then we would just say sodium ion. We don't change the ending for positive ions. So if we look at our periodic table is actually organized based on the number of valence electrons. When we look at group 1 and 2, the alkali metals and the alkaline earth metals, all of the group 1 elements have 1 valence electron. This is actually why hydrogen goes over here, even though it's a nonmetal. All of the alkaline earth metals in group 2 have 2 valence electrons. And so because they all have 1 or 2 valence electrons, depending on the column or the group that they're in, we could then predict the most likely charge they're going to take. As you can see, I've labeled this periodic table to the first column, they all take on positive 1 charges, and the second column, they all take on positive 2 charges. Just looking at the representative elements, the taller groups 1, 2, 13, 14, all the way to 18, we could very easily predict the most likely charge these atoms are going to take. The alkali metals all take on positive 1 charges, the alkaline earth metals take on positive 2 charges, strictly because the alkali metals have a 1 valence electron that they're going to lose, and then the alkaline earth metals have 2 valence electrons that they're going to lose, taking on positive 1 and positive 2 charges. If we go to the other side of the periodic table, we see that the trials, the boron group, these have 3 valence electrons, and so since they have 3 valence electrons, when they lose those 3, they become a positive 3 charge. So that's what we can expect for this column, this group. For the next group, we have the tetrals. The top ones, carbon and silicon, they have a tendency to gain 4, whereas the metals, germanium, tin, and lead, have a tendency to lose 4. If they're losing 4 electrons, they're going to be a positive 4 charge. If they're gaining 4 electrons, they're going to be a negative 4 charge. And so the tetrals, this is kind of the dividing group, or one of the dividing groups, because we know that nonmetals are more likely to gain electrons to become negative charges, so therefore the top part of this group, because it's above the dividing line, these are the ones that are more likely to get negative charges because they act more like nonmetals, carbon being definitely a nonmetal, silicon being a metalloid. If we move over to the pnictogens, group 15, these all have 5 valence electrons, and so To get to 8, they just need to gain 3 more electrons. By gaining 3 more electrons, they take on a -3 charge. And so we see -3 charges for the nitrogens. The chalcogens with oxygen, sulfur, selenium, we have 6 valence electrons. They need 8, so they take on 2 more, forming a -2 charge. And then the halogens, finally, one of the most reactive groups on the periodic table, along with the alkali metals. They have 7 valence electrons. They're 1 away from 8. They want to gain 1, forming a -1 charge. The noble gases are inert. They don't react because they don't have to gain or lose any electrons to get a full octet. They already have a full octet in their outer energy level, so therefore they're not going to take on charges because they don't ionize, because they're already satisfied with the 8. And so using the arrangement of the periodic table, we can determine the number of valence electrons that each elements have, and then from that we can determine the most likely charge these elements are going to take on. So +1, +2, +3. So metals take on positive charges, 1, 2, and 3. And then the metals in group 14 are going to take on +4 charges. The non-metals in group 14 take on -4 charges. This is kind of like these elements, since they have 4 valence electrons, do they gain or do they lose electrons to get their full octet? Because they're right in the middle. They can gain 4 or lose 4. And we find that the metals are going to have a more likelihood of forming positive charges and non-metals forming the negatives. And so once we go +1, 2, 3, 4, and so now we reverse our count and we're negative. So +4 or -4, -3, -2, -1, 0. So if you start on the edge of the periodic table, ignoring the noble gases, we go 1, and then we go in a group, it's 2, and then we go in another one, it's 3, and then 4. And so +4 and -4 are going to be some of the highest charges that you're going to have on the periodic table. I haven't mentioned anything about the transition metals or the inner transition metals, the lower groups here, because the trend is not as apparent as it is with the representative groups, the taller groups. And if you look at the trend though, +1, +2, and then +3 is over here, because the transition metals are between +2 and +3, we can expect that most of these metals are more likely to take on +2 and +3 charges, 2 or 3. There are other charges that can be taken on, but for the most part, this whole area of the periodic table is going to take on +2 and +3 charges. Some of these elements, actually many of them, are what we call multivalent species, which means they could take on different charges depending on the conditions. For example, iron can be a +2 or a +3 charge, with both +2 and +3 being common charges for iron. Copper can be +1 or +2. There's a lot of different multivalent species, a lot of different metals in this area that can take on more charges. So if you remember the sequence at the top, +1, +2, +3, +4, -4, -3, -2, -1, 0, you're going to cover most of the periodic table. One other little rule that I teach is that if you start with aluminum, as you would expect is a +3 charge. If you start with aluminum and you work your way downward diagonally, aluminum is a +3, zinc is a +2, and silver is +1. Silver, zinc, and aluminum only take on 1 charge, and it's just a 1, 2, 3 sequence. So silver is always +1, zinc's always +2, aluminum is always +3, and that will also help you out if you remember that 1, 2, 3 sequence. So that's it. Actually, let's talk briefly about the size when we form ions. And so positive ions typically decrease, or they always decrease in size when they form positive ions, because we're removing electrons. So if I go back to this slide, if you imagine if I were removing this outer electron and exposing that next layer down, it's getting smaller because it no longer has that outside layer. So as we remove electrons, the ions get smaller. So as they form positive ions, they become smaller. When we add electrons in, they're going to be getting bigger, which is the opposite of getting smaller, obviously. And it doesn't completely have to do with the removal of that layer, but it more has to do with the repulsion of the electrons and the balance between the electrons and the protons in the nucleus. And so if you remove an electron, the tug of war between the protons and the electrons start to win. And so they're pulling those electrons in more tightly. And so therefore, when something ionizes and it becomes a positive charge, it's going to become smaller. Whereas if you add in an electron, the electrons start winning that tug of war between the electrons and the protons, and they pull away from the nucleus a little bit more. And so when something becomes a negative ion, it's going to get bigger. When something becomes a positive ion, it's going to get smaller. And so here we could see positive ion, electrons being removed, protons start winning that tug of war, and so the size of the atom decreases when it's ionized. On the right side over here, we see chlorine. Chlorine's gaining an electron. The electrons start winning that tug of war between the negatives and the positives, and therefore chlorine becomes chloride and becomes much larger in size. And so positives are getting smaller, negatives are getting bigger. And so if we look at the radius trend for the periodic table, we can see that the largest atoms are at the bottom left, and the smallest ones are at the top right, and the trend is diagonally from the top right to the bottom left, increasing in size. It's the same thing when they're ionized as well, but we have this dividing line. The trend kind of resets when we're talking about the positives versus the negatives. And so the trend here is that for the positives, we're increasing in size from carbon all the way down to cesium. And so the trend is increasing from carbon to cesium, and then the trend kind of resets for fluorine. Fluorine is the smallest negative ion, and it increases in size down toward arsenic. And so we have this dividing line for the trend between the positives and the negatives between group 14 and 15. And so we can see that it's the same trend for the natural, or the normal neutral atomic radius, where you're increasing from the top right to the bottom left. But for ions, it has a reset point for that trend. It only exists within the positive ions, and it only exists within the negative ions. So that's it for ion formation. I hope this was helpful.